Okay, our next assignment is going to be 5.2, linear approximations and differentials. So your essential question, actually two questions, how do you find the equation of a tangent line at a given point? Hopefully you already have some idea about that. And what are differentials? Okay, so that's probably the new information, but really nothing new here. All right, so I'm going to start you on page 192, please. I'm going to explain the graph that is on there, and then please feel free at any time to read through this. But basically what we have here in figure 5.2c, you have the function, which is this green line, and then you have the tangent line at a certain point, c, f of c. Now, if I was to find the slope of the actual tangent line, then what I'd be finding would be this change in x over this change in y, or this dy. Okay, and that's what we're, right? That's what we find the slope of the tangent line by finding dy over dx, right? Or the slope, okay? The problem is that you're not actually finding this, when you're finding the slope of the tangent line, it's not, there's a little bit of an error between the change in y on that tangent line and the change in y on the actual function, okay? So that change in y on the actual function is going to be a little bit different, okay? So when we're finding the slope of the tangent line, we are using dy over dx, not this actual change in y that relates to the function. The change in x stays exactly the same. So we can actually say that dx is, in fact, the change in x. Okay? However, and there's a property and definition down here, next page, page 193, to really understand what the differentials are, well, dx is the exact same thing as change in x. dy is, right? So dy dx is the same thing as f prime of x, or the derivative of x, right? And so if I want dy by itself, I just solve for it by basically multiplying both sides by dx. Okay, so that is somewhat of an explanation for you, and I'll write something down here in a minute. Let's see, so if we know that the derivative of y with respect to x is the same thing as the derivative of x, right, or of f of x, or the derivative of f, then I know that dy, if I want to get dy all by itself, I'm just going to multiply both sides by dx. So really, dy is the same thing as f prime of x dx. Okay, so that's your differential dy. And then your differential dx is really the same thing as change in x. Okay, whether it's along the function or along the tangent. Okay, it's going to be the same thing. So you might want to highlight these. These are your differentials. Okay, we're going to go ahead and do some examples here. So let's start with find the equation of the tangent line to y equals 2x squared at x equals 3. Okay. So we want the equation of the tangent line, so we're always going to use, either y equals mx plus b, or maybe you want to use your point slope form. Let's see. We need our slope, right? So our slope here is going to actually come from the derivative of y with respect to x. And the derivative of y with respect to x would just be 4x. Okay, but what is the slope at x equals 3? Okay, so the slope, let's see, how can I write that? Let's do, how about, another way I could write this is y prime. Right, so maybe if I wanted actually at 3, this would be y prime of 3, which would be 4 times 3, which would be 12. So my slope, in fact, is 12. Okay, So taking that and plugging it back into here, I'm going to end up with y equals 12x plus b. Okay, well, let's see. So I was given my x value. So can I figure out what my y value is when x is 3? So that's going to involve, thinking back to, if I plug in 3, what do I get? And it looks like I'm getting 18. Okay, so this is my point right here. So I can use my slope-intercept form. I can use my point-slope form to figure out what my actual b is going to be. So let's see, this would be 18 equals 12 times 3 plus b, or 18 equals 36 plus b. So b will be negative 18. Okay, so my final equation of my tangent line at x equals 3 is going to be y equals 12x minus 18. All right. Moving on to another example. So let's do example 2. Find the equation of the differential dy. Okay, so let's do 1a. Y equals x cubed plus 2 to the 8th power. All right, so we're going to start. To get your differential, you're always going to find your derivative first, and then you're going to solve for differential dy. All right, so derivative of y with respect to x. Well, let's use my power rule first. Now I've got to chain rule that, so I'm chain ruling it, and I'm multiplying it by, let's see, 3x squared. All right, so derivative of y with respect to x is equal to, let's call that 24x squared times x cubed plus 2 to the 7th power. And now I want dy all by itself. So now I'm going to take and multiply both sides by that dx. It's that simple. Okay, so coming over here for my final answer, dy equals 24x squared x cubed plus 2 to the 7th dx. Now this becomes important because what's going to end up happening is you're going to be given a differential and you're going to have to get back to maybe the derivative or to the original function. All right, let's do another one of these. So looking at another one, y equals ln of secant x. So again, we want to find an equation for the differential dy. Okay, so starting with taking the derivative, I'm going to have 1 over secant x. Then I'm going to chain rule that. Derivative of secant x is secant x tan x. Now this is like over 1. So some stuff reduces here, right? So really secant x reduces. So I'm left with dy dx equals tan x. And if I just want to solve for the differential, I'll multiply both sides by dx. So dy equals tan x dx. So looking at page 191 in your book, there's this property, local linearity and linearization of a function. Basically, all this is saying is that if you come up with the tangent line to a function at some c, okay, so some x value, all right, and c, f of c is just the inputs and the outputs of that point where it's tangent, okay, and if that tangent line ends up with, the derivative, okay, as its slope, then anywhere really for any x value really close to c, you can get a really close approximation to what the actual output will be on the function. Okay, so that's what linearizing a function means, okay, and local linearity. Okay? Not much new there, I don't think. not much that's too hard to grasp. Okay, so I'm moving on to my next example. This is my example 3. We're going to find an equation for the antiderivative. And another word for antiderivative, so aka indefinite integral, which we've already done some of this, maybe not for a while, but you have seen this before. Okay, so I am going to give you the differential e sine x cosine x dx. Okay, and what you're going to want to do right now is you want to find an equation for the antiderivative. Okay, so the first thing I should do is figure out what the derivative is, right? So if I just divide both sides by dx, then I know that my derivative, the derivative of y with respect to x, is just e raised to the sine x cosine x. Okay, and my goal now is to now do the antiderivative, so to get back to y. Okay, so no more derivative of y with respect to x. I just want an answer for y. What was that original function that I took the derivative of to get this? Now, when you see a base e, you should realize, well, when you take the derivative of a base e, it stays exactly the same. So I'm probably going to start out with e to the sine x. Now, for me, the way that my brain works is, okay, I know that that's a part of it. Let me come over here now and try and take the derivative of that. So let me take the derivative of y with respect to x of this thing. Well, let's see, that's going to give me e to the sine x, and then I would need to chain rule that, right? And so the chain rule, if I multiply by the derivative of the inside function, will be cosine x. Well, voila. Could there have been something else here, however? Of course, there could have been a constant, right? And if I had taken, if it had been like plus 2 or whatever, if I had taken the derivative of that, it would end up being 0. So we need to definitely put it in there that we potentially could have had a constant. Okay, so pretty easy stuff there. Pretty nice review.